What specific limitations of chain of thought, COT prompting, are revealed through the use of the DATAALCHEMY framework in your experiments?
The DATAALCHEMY framework reveals several specific limitations of chain of thought, COT prompting. Firstly, COT reasoning exhibits significant fragility when faced with out-of-distribution OOD scenarios, as performance degrades sharply under moderate distribution shifts, indicating that COT relies heavily on learned patterns rather than genuine logical inference. Secondly, the experiments demonstrate that COT struggles with task generalization, failing to apply learned reasoning patterns to novel tasks or transformations, which leads to incorrect outputs even when reasoning steps appear coherent. Additionally, length generalization is limited, as COT cannot effectively handle reasoning chains of varying lengths from those seen during training, resulting in decreased performance. Lastly, format generalization shows that COT is sensitive to surface-level variations in prompts, where minor perturbations can significantly impact the correctness of the reasoning process. Collectively, these findings underscore that COT is more a sophisticated pattern-matching mechanism than a robust reasoning system.
How does the proposed method aim to dissect COT reasoning into the dimensions of task, length, and format? Please explain each dimension and its significance in your research.
The proposed method dissects chain of thought COT reasoning into three critical dimensions: task, length, and format, each revealing unique aspects of COT's performance under distributional shifts. 1. Task generalization examines how well COT reasoning can transfer across different types of reasoning tasks, particularly when faced with novel tasks that may have unique logical structures. This dimension is significant, as it highlights the model's limitations in applying learned reasoning patterns to unseen scenarios, revealing a critical threshold beyond which COT reasoning fails exponentially. 2. Length generalization investigates the model's ability to handle reasoning chains of varying lengths compared to those seen during training. This aspect is crucial because real-world problems often involve varying complexities, and our findings indicate that COT reasoning performance degrades as the length discrepancy increases, emphasizing the model's rigidity in adapting to different reasoning step requirements. 3. Format generalization assesses COT's robustness to surface-level variations in prompt formulations. This dimension is significant, as it tests whether the model has internalized flexible reasoning strategies or remains reliant on specific templates encountered during training. Our experiments show that COT reasoning is highly sensitive to format changes, which can significantly affect its correctness, underscoring the superficial nature of its reasoning capabilities. Together, these dimensions provide a comprehensive framework for understanding the boundaries of COT's effectiveness and the mechanisms underlying its apparent reasoning capabilities.
Can you provide a detailed, step-by-step explanation of how DATAALCHEMY controls for distribution shifts when training large language models?
DATAALCHEMY controls for distribution shifts by creating a synthetic dataset framework that allows for rigorous experimentation under precisely defined conditions. First, it enables the training of language models from scratch, ensuring that the models are exposed to a controlled set of data that can be systematically manipulated. The framework introduces three critical dimensions of distribution shifts: task generalization, length generalization, and format generalization, each of which is tested by varying the elements, transformations, and prompt structures used during training and evaluation. For instance, in task generalization, DATAALCHEMY assesses how well models can apply learned reasoning patterns to unseen tasks by introducing novel elements or transformations that differ from the training data. Additionally, it employs various perturbation modes to simulate real-world variations in prompt formats, allowing for a comprehensive analysis of how these shifts impact the model's reasoning capabilities. This structured approach ensures that the effects of distribution shifts on COT reasoning can be isolated and analyzed without interference from complex patterns learned during large-scale pre-training.
What metrics did you employ to assess the performance of COT reasoning in your experiments, and how do these metrics specifically highlight the shortcomings of the model?
In our experiments, we employed several metrics to assess the performance of chain-of-thought, COT reasoning, including exact match rate, Levenshtein distance, edit distance, and BLEU score. The exact match rate measures the proportion of responses that exactly match the expected answers, highlighting the model's ability to produce correct outputs. Levenshtein distance quantifies the number of edits required to change the model's output into the correct answer, indicating the degree of deviation from the expected response. The BLEU score evaluates the quality of generated text by comparing it to reference texts, emphasizing the fluency and coherence of the reasoning steps. Collectively, these metrics reveal that COT reasoning often fails to generalize effectively, as performance degrades sharply under distribution shifts, with exact matches dropping significantly and BLEU scores indicating poor alignment with expected outputs, thus underscoring the model's reliance on learned patterns rather than genuine logical inference.
In your findings, you mention that COT reasoning fails to generalize across novel task structures. Can you elaborate on how you determined the failure threshold for task generalization, specifically related to the task generalization complexity metric?
In our findings, we established the failure threshold for task generalization by introducing the task generalization complexity (TGC) metric, which quantifies the discrepancy between training and testing tasks. The TGC metric is defined as a function that incorporates various factors, including the novelty of elements and transformations encountered in reasoning chains. We identified a critical threshold, denoted as tau, such that when TGC exceeds this threshold, the probability of correct COT reasoning drops exponentially. Specifically, we formalized this relationship with the equation P text correct, C lec E caret delta text TGC C tau, indicating that as the complexity of the task increases beyond the threshold, the model's ability to generalize effectively diminishes significantly. This systematic approach allowed us to empirically validate the boundaries of COT's effectiveness in handling novel task structures.
What are the implications of your findings regarding COT prompting for future development in language models? And how should researchers proceed to ensure the development of models capable of genuine logical inference?
The findings from our investigation into chain-of-thought, COT prompting reveal that its effectiveness is largely superficial, relying on structured pattern matching rather than genuine logical inference. This suggests that future development in language models should prioritize robust out-of-distribution (OOD) testing to uncover vulnerabilities across various task, length, and format variations, rather than solely relying on in-distribution performance. Researchers should also be cautious against over-reliance on COT as a universal solution, as it can produce fluent yet logically flawed outputs, potentially leading to false confidence in model capabilities. Furthermore, while supervised fine-tuning (SFT) can temporarily enhance performance on specific distributions, it should not be viewed as a comprehensive solution for achieving true generalization. Instead, the focus should shift towards developing models that can exhibit deeper inferential competence, moving beyond mere pattern recognition to authentic reasoning capabilities.